So hello guys, in the last video I was discussing the different approaches of integration testing, right? So there are three approaches, right? The last videos also, in last video also I, I, I discussed this thing. What are those three approaches? First one is decomposition based integration, which I already discussed in the last video. So another two approaches are call graph based integration. This second approach. Third approach is path based integration. Okay, three approaches are there. First one is decomposition based integration. Under the decomposition based integration, we have top down approach, bottom up approach, sandwich approach, and big bang approach. In this call graph approach, I'm going to discuss in this video call graph as well as path-based integration. Coming to the call graph based integration, regarding the definition, this is based on program graph only. Okay, the call graph of a program is a directed graph. Okay, a simple directed graph. Graph is that people should know, right? Graph with some flow of direction. Okay, it's a directed graph here in which the nodes are nothing but unit modules. Okay, nodes are nothing but modules, right? Where in the basis per testing we observed, right? The nodes are considered as a statement of a program in that path based testing, but here in the graph based integration, nodes are nothing but a module. Okay, nodes are nothing but a module, and edges correspond to actual program calls. Okay, edges correspond to actual program calls. For example, if A calls the module B, if AB are module, if A calls the module B, then there is a edge, directed edge between A and B. Okay, in this way we should understand. Okay, this is a simple definition. Call graph based integration. Call graph is nothing but a program graph. Call is nothing but the interaction between two units by calling to each other. One, if the A needs a function of B, it will calls the it will actually calls the function B. Okay, that's why we have a edge between A and B. Okay, call graph integration avoids the possibility of impossible edges in decomposition based integration. In decomposition based integration, there may be a possibility of some complex level edges, but here there is no such kind of things will actually occur, since two edges will only occurs when if a unit actually calls another unit. Okay, can still use the notion of stubs and drivers. It actually, in small extent, we can use the notion of a stubs and drivers. Can still traverse the call graph in top-down or bottom-up approach. Here also, a, like decomposition approach, you can either follow top-down as well as top-bottom-up. Okay. So in this call graph integration, right, uh, regarding the some other points in the statement form, if we say this one, this the basic drawback of decomposition based integration is actually uh, the functional decomposition tree. That is actually that functional decomposition tree is there, right? That is actually the drawback only. Okay, it is in the form of a complex manner. Okay, if we use the call graph instead of this one, we actually mitigate this, we can actually remove this deficiency. So we also move in the direction of behavioral testing. Okay, there are two approaches of testing, right? One is structural testing, which mainly focus on structural aspects, where behavioral testing, that is actually main thing, which mainly focus on behavior of a program, how exactly the program behaves. Okay, in this way we are in a position in a position to enjoy the investment we made in the discussion of a Google graph theory. If you know the concept of graph theory, this will actually gives you basis for understanding call graph integration. Okay, since the call graph is a directed graph, why not use it in the way used in program graph? Okay, this because of this idea only, this call graph based integration works. Okay, since it is a directed graph, why can't we actually use as a program graph this one? Okay, this question leads us to two new approaches in this integration testing. We will refer to them as one is pair-wise integration, another one is neighborhood integration. Okay, what are the two approaches of call graph based integration? First one is pair based integration and the next one is neighborhood integration. Okay, so coming to the you know pair-wise integration, the idea of this pair-wise integration is what it is completely remove the concept of club stub driver development effort. There is no stub will be there, there is no driver will be there. Okay, uh, this actually uses the actual code. Okay, instead of using stubs and driver, this pairwise integration uses the actual code. At first, this maybe sounds like Big Bang integration. In Big Bang integration, there is no stubs drivers are there. At once, we're going to take all the units and we're going to club all the units at once. But there is a difference here coming to the Big Bang integration. But we restrict a session to just a pair of units in the call graph. Okay, that is actually there is a clear difference between Big Bang approach and pairwise integration approach. So in Big Bang, what is exactly Big Bang approach? We will take all the units at once and we will club all the units at the same time, and we are going to integrate to conduct the integration testing. That is Big Bang approach. Okay, but in Big Bang approach also there is no use of stubs and drivers. There we are going to use the actual code only. But instead of integrating all the module at once, here we will take two module at a time and we will actually pair those module. That's why the name pairwise integration. That's why at first that sounds like Big Bang integration, but we restrict a session to just a pair of units in the call graph. Okay, the end result is that we have one integration test session for each edge in the call graph. Okay, if uh, for each different edges are there, right? For each edge we conduct actually one integration session. That's why this is much of reduction in the sessions from either top down or bottom up. Okay, usually when conducting a SATM system, we usually have 42 sessions there. Okay, 42 times we are actually conducting the pairwise integration testing. Okay, but it is a drastic reduction in stub driver development. If of course the stub driver development is a costly process. That's why the main idea is to minimize the use of stub and driver. Instead of that one, just use the actual code. That's why this pairwise integration uses the actual code. Okay, this is the complete pairwise integration is. Okay, another integration is there. It's called neighborhood integration. So in this neighborhood integration, the name only suggests we are going to see the neighborhood nodes. We are going to integrate with the neighborhood nodes in the graph. We can let the mathematics carry us still further by borrowing the notion of a neighborhood from topology. Some mathematical concepts for that one, we define the neighborhood of a node in a graph to be the set of nodes that are one edge away from the given node, right? If there is only one edge difference between two nodes, you can call it as a neighborhood nodes. In a directed graph, of course, this means all the immediate predecessor nodes and all the immediate successor nodes, right? the immediate predecessor and the immediate successor. There are actually the 11 neighborhoods for SATM example. The SATM system, we have 11 neighborhood nodes are there. Some formula is there to find some interior nodes for the neighborhood and all. We can always compute the number of neighborhood nodes for a given call graph. Each interior node will have one neighborhood plus one extra in case leaf nodes are connected directly to the root node. Okay, an interior node has a non-zero in degree and a non-zero out degree. Okay, non-zero in degree means there is no upcoming node from other node. Out degree means there is no edge coming out of there is no edge going out of that node. Okay, so interior nodes is equal to nodes minus source nodes plus sink nodes. So the same way, if you find the interior node, then you can use this interior node in the calculation of neighborhoods. That's why neighborhoods is equal to interior nodes plus source node. Okay, if you want to find neighborhoods, the equation is interior nodes plus source node, where interior nodes is nothing but the total nodes minus source node plus sink node. Okay, for example, usually in program graph we will have more than one source node and one sink node. Assume that we have 20 nodes are there, and out of 20 nodes we have two source node as well as two sink node. So then the interior nodes will become 20 minus 2 plus 2. 20 minus 2 plus 2 means 20 minus 4 means 16. Okay, neighborhood nodes will become 60, 16 plus 2, 18. Okay, then the neighborhood will become 16 is equal, 16 plus 2 is equal to 18. Okay, so after combining all this one, you can easily you can also see like this: neighborhood is equal to nodes by minus sink node. If you don't need to, you know, mm, uh, you know, find the interior node, you can simplify the formula is equal to interior nodes is equal to nodes minus sink node. Of course, nodes in the sense 20 minus 2 again 8. This also become 8. This also become 8. Okay, sorry, 18. This also become 18. This also become 18. Okay, so this formula people need to remember while reading about neighborhood integration. Okay, so last approach, what is the last approach? Is simple approach called path based integration. So path based integration in the sense following the different path. We have different paths, right? DD path, DU path, another special path will come, path. Okay, these are all called by using this one we can conduct the integration purpose, integration approach. Okay, integration testing level construct similar to DD path for a unit testing, right? So here we're going to extend the symbiosis of specification based and code based testing to the integration level. So here the greater emphasis on behavior thread. Okay, instead of structure level thread, the concentration is going to behavior level threads. So here also shift emphasis from interface testing to interaction. Usually normally we will actually focusing on interfaces while doing integration testing, but here we are focusing on interaction, mean co-functions among unit. What are the actually interaction between different units, different model and all. Instead of interfaces, we emphasis on interaction. Okay, need some new definition actually, like source and sink nodes in the program graph. What exactly the source and sink nodes, and model execution path. What is actually generalized message means, path means and all. Okay, let us look one by one here. Here, as already told you, source node is nothing but in a program is a statement fragment at which program's execution begins. Okay, the first node is actually source node. Sink node means in a unit is a statement fragment at which program execution terminates. Where exactly the program is going to terminate? Last node only. Okay, source node is nothing but first node, sink node is nothing but last node. Okay. A module execution path is nothing but sequence of statement that begins with a source node and ends with a sink node with no intervening sink nodes. If there is no sink node, it will come between source node and sink node. That whole path is considered as a module execution path. Okay. What is message? A message is nothing but a programming language mechanism by which one unit transfer control to another unit and acquires a response from other unit. Okay. Of course, message passing, right? We are actually passing a message from one method to another method. In the same way, here also message is actually passed from one module to another module. Okay. Some another concept like regarding path-based integrations and all. Much of the progress in the development of mathematics comes from an elegant pattern. What is that elegant pattern? Have a clear idea of where you want to go. Okay. If you know where you want to go, for example, if you know your goal, if you know your aim, then your effort is half done. Only need to travel towards your goal. If you know exactly where you want to go, of course, then there is no way to become failure, right? If you know which place you want to go, directly go to that place without thinking about another thing. The same way, you should have a clear idea of where you want to go and then define the concepts that take you there, right? If you want to go for some particular place, after deciding which place, you need to decide in which way, in which approach you're going to, whether you will go by bus, go by bike, or whether you're going to use another transporting like car, bus, train, bike and all, right? That is here, once you know which place you want to go, then define the concept that actually take you there. Okay, that is actually the concept of mathematics. Here also we using the same concept here. So we do this here from path-based integration testing. Okay, that's why the name path. If you want to know exactly where you want to go, you will directly go from that particular path. So when a unit executes, when a module executes, some part of source statement is transferred, right? Of course, some part of a source statement is traversed. Suppose that there is a call to another unit along such a path. At that point, control is passed from the calling unit to the call unit, right? Of course, when there is a sequence of execution flows from one point to another point, at that level, if there is any calling statement from one module to another module, of course there is a diversion, right? Diversion of flow from that particular module to the call module, right? Where some other path of source statement is travels. Okay, this is the basic concept. There are two possibilities there. One is abandon the single entry, single exit precept and treat such calls as an exit followed by an entry, or suppress the call statement because control eventually returns to the calling unit anyway. Two approach you can follow. You can consider, or you can just abandon the single entry, single exit precept, treat such calls as an exit and just neglect that one. Otherwise, suppress the call statement because control actually returns to the calling. Either you can give control to that particular call, or you can't give that one. You just neglect that one and show the normal path. Okay, these two way only you can do. The suppression choice works well for unit testing, but it is identical or antithetical to integration testing. So suppression choice, of course, you can do for unit testing, but you can't do for integration testing. Okay. So under this path-based testing, one new approach is one new concept is there, that is called MM path. What is MM path? M is usually module, first M. Next M is usually message. So message passed from one module to another module. That's why we can call it as a method MM path. In DD path, what exactly the DD path? Decision to decision. From one decision node to another decision node, the path travels, that is called DD path. Here, the message travels from one module to another module, that is called it is MM path. Module message module path. An MM path is an interleaved sequence of module execution paths and message, of course. The basic idea of an MM path is that we can now describe sequence of module execution path that includes transfer of control among separate units. Okay, different transfer of separate units will also come here. The traditional software, what exactly MM means? Traditional, the old software. It's actually understood as module message. Okay, module message. But coming to the object-oriented concept, object-oriented software, what exactly this MM means? MM here means method message, right? In traditional approach, it is module message. In object-oriented method means method message. The message is actually transferred from one method to another method. The message is actually transferred from one module to another module. We'll take that first one approach. Okay. These transfer are by messages, therefore MM paths always represent feasible execution path, and this path cross unit boundaries. Of course, different unit boundaries are there, right? It will actually crosses from one unit to another boundary. Okay. For example, this one clear example of a method MM path across three different units. Three different models are there. You can just check the path. So 1 2 3 1 2 is the execution. After executing 2, it will directly go to 4. Instead of going to 5, there is actually a call from A to B. That's why it will directly go from 4 to A4 to B1, right? From node A4, consider it as a A4 to B1, first node of B. Again, it will travels to, again there is a call to node C. That's why it will directly go to B2 to C1. So A1, A2, B4, A1, A2, A4, B1, B2, C1, C2, C4, C5. Again, it will is transferred to B3. So B3, B4, A5, A6. It is actually the message path, MM path. Okay. Coming to another example of message path, you can just write this one. Okay, this is more than enough. If you want to know this more than enough, this just for example purpose only I have taken from another textbook here. I mean the same textbook, which is actually extended version. It's actually fourth edition of your prescribed textbook, but the second or third edition is enough for you to read. Okay, this is actually the fourth edition. One simple example just for understanding purpose. Okay, so an MM path is an interleaved sequence of model execution path and messages. MM path cross three units like this one, right? A4, B1, right? Same way. B2, C1. The same thing is actually given in this node format only, right? Same thing. Right? Same thing. MM path across three units. You can just check here. You can clearly understand. Okay. The node sequence in example path is A1. The message MM A1, A2, A3, A4, message M1 from to message to B1, B2, again message to message MSG, message 2 to C, message 2 will return. The same thing is actually given here, B4, B3, B2, B3, B4, message 1 again going to return to X6, A7, A8. Note that B2, B3, B4 is a green star notation of repeating travels of the loop. Okay, same thing is actually given here, this same thing. Okay, it's actually explained in statement format. Okay. If you want to know about MMPath again, message questions, okay, questions, non-trivial MMPath, there is always at least one, there is always at least a point at which no further messages are sent, okay. Of course, there should be some end to anything, right? That's why for this message also, messages transfer also, there is actually some particular end is there. So in the example of MMPath unit C, right? Unit C is the point of message questions, message endpoint here. Just check here. From unit C, there is no other transfer, right? It will directly the transfer is written to B here. Again from B, the transfer is written to E1. There is no other path like D, A, B, C, D, E, F, and all. Only C. At C only endpoint is actually we get the endpoint here. Okay. So in a data-driven program, like next-state function and all, MMPath begin with the main program only. In all the in all the data-driven program, MMPath actually start with main program. So in an event program, there are one is data-driven program, another one is event program. MMPath begin with the unit that senses an input event and end in the method that produces the corresponding output unit. Okay, so data driven means something like program, C program and all. Of course, it will start from main program. Event driven, like the windshield wiper, some event activity, right? Some event activity occurs, right? In this case, the point where you actually senses the input, right? If you give input to your program, that point is considered as a starting point. When you actually getting the output, that is considered as a endpoint. Okay. Some other sequence will come like ready path sequence source element and all. These are actually out of syllabus for just understanding purpose. So if you want to again see, ready path is a sequence of source statements. Unit execution path is sequence of ready path, where MM path is a sequence of unit execution path. Okay, this is actually model execution. A system of thread is a sequence of MM path. Okay, these are all some important another important consequences sequences. Okay, now if you want to know the cyclomatic complexity also, you can check here. No need to know about cyclomatic complexity and regarding MM path and all. Okay, uh, this will actually ends your module 5. Okay, so all the best for your exam. Okay, if you know, uh, if you have any doubts regarding any model, please let me know. I will explain the concept once. If we get back to the college again, I will repeat this process. I will reverse the important concepts. I will discuss the important question, and I will again make revision of the important concept. Okay, thank you.